Now, in this lecture, we'll answer on two questions. In the first question, we'll find out the length of line 7DE that is equal to x. And in the second question, we'll find out the shaded area, the value of the shaded area that is inside the quarter circle. Okay, so we'll start with the first question. In the drawing we have triangle ABC. Angle ABC equals to 30 degrees. Angle ACB also equals to 30 degrees. And angle DAE equals to 60 degrees. Line segment BD equals to 5 units. Line segment EC equals to 4 units. And our mission is to find out the value of line segment DE that is equal to x. Okay, so first of all, we focus on triangle ABC. In triangle ABC we have two equal angles. Those two angles are equal to each other. That is to say that they are both equal to 30 degrees. Okay, so inside triangle ABC, we have angle ABC. This angle equals to this angle, this is actually angle ACB, and they are both equal to 30 degrees. I'll repeat again, in the right triangle ABC, angle ABC equals to angle ACB. I'll repeat again, angle ABC equals to angle ACB, and both angles they are equal to 30 degrees. And according to the rule that in front of equal angles in the triangle there are equal sides, we get that in front of this angle we have side AB, in front of this angle we have side AC, and according to the rule that I mentioned, side AB must be equal to side AC. AB equals to AC. Now here, those two sides they are equal to each other according to the rule that I mentioned. We define angle BID as alpha, and we define angle EAC as beta. And we know that the sum of the angles in any triangle, and especially in triangle ABC, is equal to 180 degrees. So here we get that this angle that is 30 degrees plus this angle that is also equal to 30 degrees in its side, plus this angle that is equal to alpha according to our definition, plus this angle that is equal to 60 degrees according to what is given us in the question, plus this angle that is equal to beta according to our definition. In total, the sum of those two angles must be equal to 180 degrees. So here we have 30 degrees plus 30 degrees is 60 degrees, and 60 degrees plus 60 degrees is 120 degrees, plus alpha plus beta is equal to 180 degrees. Here we subtract 180 degrees from this equation, and we get that 180 degrees minus 180 degrees is 0, so here alpha plus beta equals to 180 degrees minus 120 degrees is 60 degrees. So if I know that alpha plus beta equals to 60 degrees, in the next step we will make construction for the vertex A. We draw a straight line in such a way that the angle that will be created will be equal to alpha. Here, so in point A, we draw the straight line in such a way that angle CAL, this angle will be equal to alpha. So angle CAL equals to alpha according to our construction, and for the vertex C we draw a straight line in such a way that the angle that will be created here will be equal to 30 degrees. So this angle equals to 30 degrees according to our construction. Then we'll extend the straight line that we draw here until it intersects with the first straight line that we drew. So we'll extend also AL until the two straight lines intersect with each other. And we'll define the intersection point between the two straight lines that we draw as point F. Okay, so actually we created here triangle AFC. In the next step we will prove that this triangle ABD is congruent to triangle AFC. Okay. So we prove the triangle ABD, this triangle a triangle AFC, this is triangle AFC. So we'll prove that those two triangles can go into each other. So why those two triangles can go into each other? Those two triangles can go into each other. First of all, those two angles, they are both equals to alpha, therefore they are equal to each other. So can I know that angle BAD, this angle, is equal to this angle that is actually angle CAF. And both angles are equal to alpha, therefore they are equal to each other. Okay, angle BAD equals to angle CAF, and they are both equal to alpha, therefore they are equal to each other. In addition, those two sides are equal to each other according to what we already proved. So side AB equals to side AC. AB equals to AC. And finally, those two angles, they are both equal to 30 degrees, therefore they are equal to each other. So here angle ABD, this angle is equal to this angle that is actually angle ACF. And they're both equal to 30 degrees, therefore they're equal to each other. I'll repeat again, angle ABD equals to angle ACF, and they're both equal to 30 degrees, therefore they're equal to each other. Actually, we proved that triangle ABD congruent, this is the sign of congruent, to triangle AFC according to side angle rule. Angle side angle rule. I repeat again. We proved that those two angles and the side that attached to it, that is AB in triangle ABD, congruent to those two angles, and the side that attached to them in triangle AFC. Therefore, we proved that those two triangles can go into each other according to angle side angle rule. And from the fact that those two triangles can go into each other, we conclude that side BD equals to side FC. BD equals to FC. BD equals to FC according to the rule that corresponding sides and congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding sides, that is to say BD and FC, will be also equal to each other. But according to what is given as the question, BD equals to 5 units. So we can write here that BD equals to 5 units. And from this equation 5 equals to BD equals to FC, we derive that FC is also equals to 5 units. FC is also equals to 5 units. In addition, from the fact that those two triangles can go into each other, we conclude that side AD equals to side AF. Side AD equals to side AF. Again, side AD equals to side AF according to the same rule that corresponding angles in congruent triangles are equal to each other. So if we define side AD as A, here side AD equals to A according to our definition, then from this equation A equals to AD equals to AF, we derive that AF is also equals to A. Here AF is also equals to A. Okay? In the next step, we join points E and F together by a straight line. In triangle EAF, this angle equals to alpha plus beta, but we have already found out that alpha plus beta equals to 60 degrees, so we can write here that this angle equals to 60 degrees. Okay, in the next step, we will prove that those two triangles can go into each other. So actually we will prove that the green triangle ADE is congruent to the orange triangle AFE, and prove that those two triangles can go into each other. So why the green triangle is congruent to the orange triangle? I write it down. We will prove that the green triangle ADE congruent to the orange triangle, triangle AEF. Find those two triangles congruent to each other. First of all, those two sides, they are both equal to A, therefore they are equal to each other. So we can write down that AD equals to AE equals to A. Repeat again. Side AD equals to side AE equals to A. In addition, those two angles, they are both equal to 60 degrees, therefore they are equal to each other. So angle DAE, this angle, is equal to this angle that is actually angle EAF. And they are both equal to 60 degrees, therefore they are equal to each other. I'll repeat again. Angle DAE equals to angle EAF equals to 60 degrees. And finally, side AE is a common side, it belongs to both triangles, so this side equals to itself. AE equals to AE is a common side. I repeat again, side AE equals to side AE is a common side. So we actually proved that the green triangle, triangle ADE, congruent to the orange triangle, triangle AEF, according to side angle side rule. Okay, I'll repeat again. Those two triangles can go into each other according to side angle side rule. Those two sides and the angle that included between them, that is to say this angle in the green triangle, congruent correspondingly to those two sides and the angle between those two sides in the orange triangle. Therefore, those two triangles can go into each other according to side angle side rule. And from the fact that the green triangle congruent to the orange triangle, we will conclude that those two sides are equal to each other. That is to say, side DE equals to side EF. I'll repeat again, from the fact that the green triangle congruent to the orange triangle, we conclude that DE equals to EF according to the same rule that corresponding sides in congruent triangles are equal to each other. But according to what is given in the equation, DE equals to X. That is the side, the line segment that we are looking for. It is equal to X. And from this equation, X equals to DE equals to EF, we will derive that EF is also equals to X. EF is also equals to X. EF equals to X. So in the next step, I will present to you the law of cosines and we will implement the law of cosines in this triangle, triangle EFC. So what is the law of cosines? The law of cosines is true in any triangle. So in any triangle, if we have this triangle, triangle ABC, it could be any triangle. This This is triangle ABC. And we know that side AB equals to A units in its length, side AC equals to B units in its length, and the angle between side AB and side AC is theta, and side BC equals to C units in its length. Then, according to the law of cosines, we get that C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. I will repeat again. In any triangle ABC could be any triangle, so the following equation is true, that C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. So we can actually implement the law of cosines in triangle EFC. So I copy triangle EFC in this page and we implement the law of cosines in this triangle EFC. Angle ECF, this angle is equal to 30 degrees plus 30 degrees, that is to say it is equal to 60 degrees. Side FC equals to 5 units, side EF equals to X, that is the line segment that we are looking for, and side EF equals to 4. So this is triangle EFC that I copied EFC that I copied from the original drawing. So in triangle EFC, this triangle EFC, according to the law of cosines, we'll get that x squared equals to 4 squared plus 5 squared minus 2 times 4 times 5 times cosine 60 degrees. I repeat again, according to the law of cosines, we get that in triangle EFC, x squared equals to 4 squared plus 5 squared minus 2 times 4 times 5 times cosine 60 degrees. So we actually found out that x squared equals to 4 squared, that is 16, plus 5 squared, that is 25. Here 4 times 5 is 20 and 20 times 2 is minus 40. This is minus 40. It is 40, but we have here minus before it, so it is minus 40. Times cosine 60 degrees, and cosine 60 degrees equals to 1/2. So we substitute cosine 60 degrees by 1/2. So we got here that x squared equals to 16 plus 25 is 41, minus 40 over 2 is minus 20, so 41 minus 20 is 21. So we found out that x squared equals to 21. Here we take a root out of this equation and we get that x equals to the square root of 21. It's actually the positive square of 21 because x is a length and the length must be a positive number. Or in terms of numbers, it is equal to 4.58 units. So here we found out that x equals to either square root of 21 units, the positive root of 21, or in terms of numbers, it is equal to 4.58 units. Okay, I write it here, x equals to either the positive square of 21, or in terms of numbers it is equal to 4.58 units. So we finished with the first question. In the next step I will present to you the second question. Okay. In the drawing we have this quarter circle. Inside this quarter circle we have a circle with radius 2. The circle is tangent to the quarter circle at this point. This is the point of tendency. And we have also this semicircle with radius that is also equal to 2 units. The semicircle is tangent to the circle at this point, and our mission is to find out the shaded area. So first of all, because of the fact that this is a quarter circle, then this point must be the center of the quarter circle, and this angle must be equal to 90 degrees. It is true in any quarter circle. Okay. And if this point is point D, so OD, tangent OD is tangent to this circle at point N. Point N is the point of tendency. Point N is the point of tendency of tangent OD with this circle. And according to what is given as the question, if we define the center of this circle as point P, here the radius Pn, that is equal to 2 units. First of all, the radius is Pn because it starts from the center of the circle, that is to say from point P, and ends at point N, that is the point of the circle itself. This is exactly the definition of a radius. So the radius Pn, that is equal to 2 units, it is drawn to the point of tendency. And we have a rule number 1 that a tangent to a circle is perpendicular to the radius drawn to its point of tendency. OM is the radius, M is the point of tendency of tangent AB with this circle. We have the radius OM that is drawn to the point of tendency. That is to say, it is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. So if AB is perpendicular to MO, that means that this angle equals to 90 degrees, and this angle also equals to 90 degrees. So we can implement rule number 1 in our drawing. So in our drawing, we have the radius Pn that is drawn to the point of tendency. That is to say, it is drawn to point N, that is the point of tendency of tangent OD with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent OD will be perpendicular to the radius NP. So if AOD is perpendicular to NP, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule number 1. Okay? In the next step, from point P, that is the center of this circle, we'll draw perpendicular on the M. This will be the center of the semicircle will be defined as point M. So from point P, that is the center of the circle, we draw perpendicular on OM. Okay? So this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. Okay? We'll define the touching point of the perpendicular from point P and MO as point H. So in quadrilateral OHPN, we have 1, 2, 3 right angles. Okay, write it down. In quadrilateral OHPN, we have 3 right angles, and the sum of 3 right angles is 90 times 3 is 270 degrees. So 270 degrees plus the size of the fourth angle, that is actually angle HPN. This angle, in total, the sum of those 4 angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Okay? So here we subtract 270 degrees from this equation, and we get that the missing angle HPN is equal to 360 degrees minus 270 degrees, it is equal to 90 degrees, it is a right angle. So we found out that this angle, it is a right angle. So actually, all 4 angles inside quadrilateral OHPN are right angles, therefore quadrilateral HOPN must be at least a rectangle if not a square, because it has 4 right angles. According to the rule that any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we will relate to quadrilateral HOPN as a rectangle. Repeat again, quadrilateral OHPN is a rectangle because it has 4 right angles, and we know that the opposite sides of a rectangle are equal to each other. That is to say, PN equals to edge O. PN equals to edge O. But PN equals to 2 units. It is the radius of the circle. It is equal to 2 units. So here PN equals to 2. And from this equation, 2 equals to PN equals to edge O. We derive that edge O is also equals to 2 units. Here edge O equals to 2 units. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we get that in rectangle HOPN, side edge P must be equal to side ON. HP equals to ON. HP equals to ON according to the rule that the opposite sides of a rectangle are equal to each other. So if we define HP as X, if HP equals to X according to our definition, Then from this equation x equals to HP equals to ON, we'll conclude that ON is also equals to x. ON equals to x. So we can write here that ON equals to x. And according here, the circle is tangent to the quarter circle at this point. So the circle and the quarter circle have an internal length between them at this point. This is the touching point between the circle and the quarter circle. And we know that whenever two circular shapes have an internal length between them, then the straight line that joins its centers must pass through the touching point of the two circular shapes. Repeat again, whenever two circular shapes have an internal length between them, then the straight line that joins their centers together must pass through the touching point of the two circular shapes. So here point O is the center of the quarter circle. Point P is the center of the circle. And according to our rule, according to the rule that I mentioned just right now, the straight line OP that connects the two centers together must pass through the touching point. And this is the touching point between the quarter circle and the circle. So we define the touching point as point K. That is to say, according to the rule that I mentioned, actually OPK is one straight line. OPK is one straight line. You can write down here that OPK, line segment OPK, is one straight line. Okay? If line segment OPK is one straight line, so here point O is the center of the quarter circle. Point K is the point of the quarter circle itself. That is to say, this is exactly the definition of a radius. That is to say, OK is the radius of this quarter circle. Okay? So, OK is the radius of the quarter circle. And we'll define the radius of the quarter circle as capital R. Therefore, OK equals to capital R, that is the radius of the quarter circle according to our definition. Here, point P is the center of the circle, according to our definition. Point K is the point of the circle itself. That is to say, PK is the radius of this circle that is equal to 2 units according to what is given as the question. So PK equals to 2 units. And what is the length of OP? What is the length of OP? Line segment OP it is very easy to see from the drawing that line segment OP equals to OK minus PK. OK minus PK equals to the length of line segment OP. So OP equals to OK. OK is the radius of the quarter circle, that is to say it is equal to capital R according to our definition. Minus PK. PK equals to 2 units. It is the radius of the circle. So in conclusion, we found out that OP equals to capital R minus 2. OP equals to capital R minus 2. So we can write here that OP equals to capital R minus 2 units. Okay, now we can implement the Pythagoras theorem on the right triangle, triangle OPN. So I copy the right triangle, triangle OPN in a new page, and we will implement the Pythagoras theorem on the right triangle, triangle OPN. The hypotenuse OP equals to R minus 2 according to what we just right now found out. Side ON equals to X, and PN equals to 2 units. It is the radius of the circle according to what is given as the question. So this is the right triangle, triangle OPN, that I copied from the original drawing. So we'll implement the Pythagoras theorem. By PT is the equation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is OP. Therefore, the square of the hypotenuse is OP squared, and it is equal to the sum of the squares of the perpendiculars. That is to say, it is equal to ON squared plus PN squared. Okay, so here OP equals to capital R minus 2, so OP squared equals to capital R minus 2 squared, and it is equal to ON squared. ON equals to X, so ON squared is X squared plus PN squared. PN equals to 2, so PN squared is 2 squared, that is 4. Here we will open the brackets on this side of equation number 1, and we will get that according to equation number 1, R minus 2 squared equals to R squared plus 2 squared, that is 4, minus 2 times R times 2, it is minus 4R, that is equal to X squared plus 4. Here we have 4 on both sides of equation number 1, so 4 will get cancelled. And what is left from equation number 1 after we cancelled 4? What is left is here we have X squared on the one side of the equation, on the other side of the equation we have R squared minus 4R. So in conclusion, we found out that according to equation number 1, X squared equals to R squared minus 4R. Okay? Here we have an external lunge between the circle and the semicircle. Those two circles touching each other at this point externally, therefore we have an external lunge between those two circular shapes. And whenever you have an external lunge between two circular shapes, then the straight line that joins their centers together must pass through the touching point of the two circular shapes. That is to say, M is the center of the semicircle, P is the center of the circle, and the straight line that connects the two centers together, it is MP, and this straight line MP must pass for this touching point. We'll define the touching point as point L. So here the straight line MP must pass for the touching point that is point L. So here we have okay, so you can see here the straight line MP that joins the two centers together passes from point L, that is the touching point of the circle with the semicircle. So we know that MLP is one straight line, so I write down that line segment MLP is one straight line according to the rule that I mentioned just right a minute ago. MLP is one straight line. Okay. Point P is the center of the circle. Point L is the point on the circle itself. This is exactly the definition of a radius. That is to say, PL is the radius of this circle that is equal to 2 units according to what is given as the question. Here, point M is the center of the semicircle. Point L is the point of the semicircle itself. This is exactly the definition of a radius. That is to say, ML is the radius of this semicircle that is also equal to 2 units according to what is given as the question. So the length of the straight line MLP, it is equal to ML plus LP. That is to say, here I write down that the straight line MLP equals to ML plus LP. I repeat again, the straight line MLP equals to ML plus LP. So the straight line MLP equals to ML, that is 2 units, plus LP, that is also 2 units. So in conclusion, we found out that the straight line MLP equals to 2 plus 2, that is 4. So MLP equals to 4. So instead of writing MLP, we can write exactly directly that is MP, because it is anyway a straight line. So we can write down that MP equals to 4 units. MP equals to 4 units. It is one straight line, of course. In the next step, so here we define this point as point Z. Point O is the center of the quarter circle. Point Z is the point on the quarter itself, so that is to say OZ equals to capital R. OZ equals to capital R, it is the radius of the quarter circle. Point M is the center of the semicircle. Point Z is the point on the semicircle itself, that is to say MZ is the radius of the quarter circle that is equal to 2 units according to what is given as the question. And what is the length of line segment MH? What is the length of line segment MH? From the drawing it is very easy to see that MH, the length of line segment MH is OZ, that is the radius of the quarter circle, minus ZM, that is the radius of the semicircle, minus edge O. Repeat again, the length of line segment MH equals to OZ minus ZM minus HO. So actually we found out that the length of line segment MH, it is equal to OZ. OZ is the radius of the quarter circle that is equal to capital R according to our definition. Minus Zm. Zm equals to 2 units according to what we have already found out. And HO also equals to 2 units according to what we have already found out. So in conclusion, we found out that the length of line segment MH is equals to capital R minus 2 is minus 4. So MH, in conclusion, MH equals to R minus 4, or capital R minus 4. So we can write down here that MH equals to capital R minus 4. In the next step, we will implement the Pythagoras theorem on the right triangle, triangle MHP. So I copy the right triangle, triangle MHP in a new page, and we will implement the Pythagoras theorem on this triangle, triangle MHP. Okay, we have angle MHP equals to 90 degrees. It is a right angle. The hypotenuse MP equals to 2 plus 2, that is 4. HP equals to X. And we just found out that MH equals to capital R minus 4. So in the right triangle, triangle MHP, by PT, equation from Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. This will be equation number 2. The hypotenuse is MP. This is the hypotenuse MP. So the square of the hypotenuse is MP square. That is equal to the sum of the squares of the perpendiculars. That is to say, it is equals to MH square plus HP square. Okay, so I found out that MP is 4, so MP square is 4 squared, that is 16, and it is equals to MH square. MH is R minus 4, so MH square is R minus 4 squared, plus HP square. HP equals to X, so HP square is X squared. So in conclusion, we found out that according to equation number 2, 16 equals to R minus 4 squared plus X squared. Here we'll open the brackets on this side of equation number 2, and we'll get that according to equation number 2, 16 equals to R minus 4 squared is R squared, plus 4 squared, that is 16, minus 2 times R times 4 is minus 8R, plus X squared. Here we have 16 on both sides of the equation, so 16 will get cancelled. And what is left from equation number 2 after we cancelled 16? What is left, it is actually in this side of the equation we have 0, that is equals to R squared minus 8R plus X squared. Here we'll add 8R to this equation, equation number 2, and we'll get that according to equation number 2, 8R equals to R squared plus X squared. Here we'll subtract R squared from this equation, equation number 2, and we'll get that according to equation number 2, 8R minus R squared equals to X squared. Okay, this is equation number 2, but according to equation number 1, we have already found out that X squared equals to r squared minus 4r. Okay, so we have two expressions for x squared, equation number 1 and equation number 2. Now we create equation number 3 that states that x squared according to equation number 1 must be equal to x squared according to equation number 2. So x squared according to equation number 1 is r squared minus 4r, while x squared according to equation number 1 is 8r minus r squared. Here we'll add r squared to this equation, equation number 3, and we get that according to equation number 3, r squared plus r squared is 2r squared minus 4r equals to 8r. So here we will add 4r to this equation, equation number 3, and we'll get that according to equation number 3, 2r squared equals to 8r plus 4r is 12r. So here we divide equation number 3 by 2, and we get that according to equation number 3, two r over 2 is r, 2r squared over 2 is r squared, that is equal to 12r over 2 is 6r. Here we subtract 6r from this equation, equation number 3, and we get that according to equation number 3, r squared minus 6r equals to 0. We'll take a root out of this equation, equation number, we'll take a common factor r from this equation, equation number 3, and we'll get that according to equation number 3, here r is a common factor of these two expressions. What is left from r squared after we took from it r as a common factor? What is left? It is actually r. And what is left from minus 6r after we took from it r as a common factor? What is left? It is actually 6. So in conclusion, we found out that r times r minus 6 equals to 0. Here we have two solutions that are possible to this equation. Either r equals to 0, but r, that is the radius of the quarter circle, can never be equal to 0. So we cancel this solution. It is impossible. So we'll focus on the other solution, that r minus 6 equals to 0. So we'll add 6 to this equation, and we get that r equals to 6. So we found out that the radius of the quarter circle equals to 6 units. And what is the value of the shaded area? The value of the shaded area, the shaded area will be equal to the area of the quarter circle minus the area of the circle minus the area of the semicircle. I repeat again, the value of the shaded area equals to the area of the quarter circle minus the area of the circle minus the area of the semicircle. So actually we found out that the shaded area that we are looking for, it is equals to the area of the quarter circle, and the area of any quarter circle equals to the area of the circle, that is pi r squared. over 4, of course, minus the area of the circle. We know that the radius, the area of any circle is pi r square, and r equals to 2, so it is pi 2 square minus the area of the semicircle. The area of any semicircle equals to the area of the circle over 2. And the area of the circle is pi r square, and r equals to 2, so it is pi 2 square. And the area of the semicircle will be equal to pi 2 square over 2. Okay? So here we know that the radius of the quarter circle capital R equals to 6, and r square is 6 squared, that is 36. In conclusion, the area of the quarter circle in total equals to 36 pi over 4 minus the area of the circle, that is 2 square times pi. 2 square is 4, and 4 times pi is 4 pi, minus the area of the semicircle, that is pi 2 square over 2. 2 square is 4, and 4 over 2 is 2, so in total this expression equals to 2 pi. So actually we found out that the area of the shaded area equals to the area of the quarter circle, that is 36 pi over 4. 36 over 4 is 9. So this expression in total equals to 9 pi, that is to say it is the area of the quarter circle minus the area of the circle, that is 4 pi, minus the area of the semicircle, that is 2 pi. This is actually the area of the value of the shaded area. Okay? So 9 pi minus 4 pi is 5 pi, and 5 pi minus 2 pi is 3 pi. So in conclusion, we found out that this shaded area equals to either 3 pi square units, or in terms of numbers it is 9.42 square units. Okay? So in the next step I will summarize the lecture. We'll start with the first question, of course. In the drawing, we have triangle ABC. Note that angle ABC equals to 30 degrees, angle ACB also equals to 30 degrees, and also angle DAE, this angle equals to 60 degrees. Side BD equals to 5 units, side EC equals to 4 units, and our mission is to find out the length of line segment DE that is equal to x, according to what is given as a question. So first of all, we focus on triangle ABC. In triangle ABC, we have two angles that are equal to each other, they are both equal to 30 degrees. Here, angle ABC equals to angle ACB equals to 30 degrees. And according to the rule that in front of equal angles in a triangle there are equal sides, you get that in front of those two equal angles there are equal sides. In front of this angle we have side AC, in front of this angle we have side AB, and that according to the rule that I mentioned, AB equals to AC. Okay, here AB equals to AC. We continue to focus on the right triangle, on triangle ABC. We define the angle BAD as alpha and the angle EAC as beta. And we know that the sum of the angles in any triangle is equal to 180 degrees, and especially in triangle ABC, the sum of its angles is equal to 180 degrees. So here, 30 degrees plus 30 degrees plus angle alpha plus 60 degrees plus beta, in total must be equal to 180 degrees. Here, the sum of the angles in triangle ABC equals to 180 degrees. Here, 30 degrees plus 30 degrees is 60 degrees, and 60 degrees plus 60 degrees is 120 degrees. So in this side of the equation, we have 180 degrees plus alpha plus beta, that is equal to 180 degrees. We subtracted 120 degrees from this equation, and found out that here 180 degrees minus 120 degrees, it is 60 degrees. So in conclusion, we found out that alpha plus beta equals to 60 degrees. Then we made a construction from point A here, from this point here, from point A, we do a straight line in such a way that angle CAF will be equal to alpha, so this angle equals to alpha according to our construction. And then from point C, we do a straight line in such a way that angle ACF will be equal to 30 degrees. Okay, so this angle equals to 30 degrees, and this angle equals to alpha, both according to our construction. So in this way, we created triangle AFC, and in the next step, we proved that this triangle AFC that we created is congruent to this triangle ADB. Okay, the triangle ABD is congruent to triangle AFC. Why those two triangles congruent to each other? First of all, here actually it is triangle ABD that congruent to this triangle AFC, okay? Why those two triangles congruent to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. Here, angle BAD equals to angle CAF, they are both equal to alpha, therefore they are equal to each other. In addition, we know that side AB equals to side AC. So here, side AB equals to side AC, and finally, those two angles, they are both equal to 30 degrees, therefore they are equal to each other. So that is to say, angle ABD equals to angle ACF equals to 30 degrees. Those two angles are both equal to 30 degrees, therefore they are equal to each other. So we proved that those two triangles can go into each other according to angle side angle rule. We have side AB and the two angles that are attached to it in triangle ABD that can go to side AC and the two angles that attach to it in triangle AFC. Therefore, those two triangles can go into each other according to angle side angle rule. And from the fact that those two triangles can go into each other, we will derive that side BD equals to side FC. Those two sides are equal to each other according to the rule that corresponding sides in congruent triangles are equal to each other. But side BD equals to 5 units according to what is given as the question. And from this equation, 5 equals to BD equals to FC, we derive that FC also equals to 5 units. Here, FC also equals to 5 units. In addition, because of the fact that those two triangles can go into each other, we derive that AD equals to AF. Side AD equals to side AF according to the same rule that corresponding sides and congruent triangles are equal to each other. So if we define side AD as A, side AD equals to A according to our definition, so from this equation A equals to AD equals to AF, we will derive that, we conclude that AF also equals to A. AF also equals to A. In the next step, we proved that the green triangle is congruent to the orange triangle. So why those two triangles can go into each other? First of all, we know that alpha plus beta equals to 60 degrees. So therefore, this angle alpha plus beta, angle EF that is equal to alpha plus beta, it is equal to 60 degrees. Okay? So we know that side AD, we just right now found out that side AD equals to side AF equals to A. So those two sides are equal to each other. In addition, those two angles are both equal to 60 degrees, therefore they are equal to each other. And finally, side A is a common side that belongs to both triangles, so this side equals to itself. So we actually proved that those two triangles can go into each other according to side angle side rule. Those two sides, side AD and side AF, and the angle between those two sides in the green triangle can go into side AE and side AF, and the angle between those two sides in the orange triangle. So those two triangles can go into each other according to side angle side rule. And from the fact that those two triangles can go into each other, we'll conclude that DE equals to EF, according to the rule that corresponding sides in congruent triangles are equal to each other. Okay? DE equals to EF, according to the rule that corresponding sides in congruent triangles are equal to each other. But side DE equals to X, according to what is given in the question. Here side DE equals to X. So we can, from this equation, X equals to DE equals to EF, we will derive that EF is also equals to X. EF is also equals to X. In the next step, I presented to you the law of cosines, and we implemented the law of cosines in triangle EFC. So what is the law of cosines? The law of cosines is true in any triangle. So if we have this triangle, triangle ABC, that could be any triangle. And we know that side AB equals to A units in its length, side AC equals to B units in its length, and side BC equals to C units in its length, and the angle between side AB and side AC is theta. Then according to the law of cosines, we get that C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. Again, C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. We implemented the law of cosines in triangle EFC, so I copied triangle EFC in this new page, and we implemented the law of cosines in this triangle. Side EF equals to X, side EC equals to 5, and side EC equals to 4 units, and the angle between side EFC and EC is 60 degrees. So according to the law of cosines, we get that X squared equals to 4 squared plus 5 squared minus 2 times 4 times 5 times cosine 60 degrees. Okay, so X squared equals to 4 squared, that is 16, plus 5 squared, that is 25, minus 4 times 5 is 20, and 20 times minus 2 is minus 40, times cosine 60 degrees, and cosine 60 degrees is 1/2. So in conclusion, this expression equals to minus 40 times 1/2. So in conclusion, we found out that X squared equals to 16 plus 25 minus 40 over 2. So 16 plus 25 is 41, and minus 40 over 2 is minus 20. So in conclusion, we found out that X squared equals to 41 minus 20, and 41 minus 20 is 21. So in conclusion, we found out that X squared equals to 21. We took a root out of this equation, and we found out that X equals to either the positive root of 21, or in terms of numbers, it is equal to 4.58 units. I'll repeat again. We actually found out that the 9 segment DE that is equal to X, it is equal to either the positive square root of 21, or in terms of numbers, it is equal to 4.58 units. We finished with the first question, then I presented to you the second question. The second question, in the drawing we have a quarter circle. Inside this quarter circle we have a semicircle and a circle. The semicircle and the circle are touching each other at point L, and the circle and the quarter circle are tangent to each other at point K. And our mission is to find out the shaded area, the value of the shaded area. So first of all, because of the fact that this is a quarter circle, it means that point O is the center of the quarter circle, and this angle ZOD equals to 90 degrees. Okay? And here OD is tangent to the circle at point N. Point N is the point of tendency. And according to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. Here the radius OM, it is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. So if AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle equals to 90 degrees according to this rule number 1. We implemented rule number 1 in our drawing. We have the radius PN that is drawn to the point of tendency. That is to say, it is drawn to point N, that is the point of tendency of tangent OD with this circle. And whenever a radius that is drawn to the point of tendency, then tangent OD will be perpendicular to the radius NP. So if OD is perpendicular to NP, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule number 1. Okay, so we have here two right angles, and from point P we draw perpendicular on MO, so this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. So actually in quadrilateral P edge ON we have 1, 2, 3 right angles. And the sum of right angles is 90 times 3 is 270 degrees. 270 degrees plus the size of the fourth angle, in total they must be equal to 360 degrees. I repeat again, that is quadrilateral OHPN. The sum of three angles is 270 degrees plus the size of the fourth angle, in total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Here we subtracted 270 degrees from this equation, and we found out that the missing angle HPN equals to 90 degrees. So this angle, it is a right angle. So we actually found out that inside quadrilateral OHPN we have 4 right angles. And any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we relate to quadrilateral OHPN as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. So in rectangle HPON, side PN must be equal to side edge O. PN equals to edge O. But we know that PN is the radius of the circle, that is equal to 2 units according to what is given us the question. So from this equation 2 equals to PN equals to OH, we derive that OH or edge O also equals to 2 units. Here edge O equals to 2 units. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, so in rectangle HPON we'll conclude that HP equals to ON. HP equals to ON, so if you define HP as X, then from this equation X equals to HP equals to ON, we derive that ON also equals to X. ON also equals to X. Okay? So here we have an internal lunge between the circle and the quarter circle. That is to say, they are touching each other internally at point K. Point K is the point of tendency of those two circular shapes. And according to the rule that whenever you have an internal notch between two circular shapes, then the straight line that joins their centers must pass through the point of tendency between the two circular shapes. The center of the quarter circle is point O, and the center of the circle is point P. So the straight line that joins the two centers together is OP, and according to the rule that I mentioned, the straight line OP must pass through the touching point that is point K. That is to say, OPK is one straight line. Okay, according to the rule that I mentioned, that whenever you have an internal notch between two circular shapes, then the straight line that joins their centers must pass through the touching points of those two circular shapes. Therefore, we can derive from it that OPK is one straight line. Okay, OPK is a one straight line. Point O, so OK is a straight line. Point O is the center of the quarter circle. Point K is the point of the quarter circle itself. This is to say, this is exactly the definition of a radius. So OK is the radius of this quarter circle that is equal to R, capital R, according to our definition. So OK is the radius of the quarter circle that is equal to capital R according to our definition. So OK equals to capital R. Point P is the center of the circle. Point K is the point on the circle itself. So this is exactly the definition of a radius. That is to say, PK is the radius of this circle that is equal to 2 units. So in conclusion, we found out that OK equals to capital R, that is the radius of the quarter circle. PK equals to 2 units, that is the radius of the circle. And what is the length of line segment PD? It is very easy to see from the drawing that PO, the length of line segment PO, this line segment, it is equal to OK minus PK. Again, OK minus PK equals to PO. Okay, OP equals to OK minus PK. OP equals to OK minus PK. So OP equals to OK, that is capital R, that is the radius of the quarter circle, minus PK, that is equals to 2 units, that is the radius of the circle. So in conclusion, we found out that OP, this line segment OP equals to capital R minus 2. So I copied the right triangle OPN in this page, and we implemented the Pythagoras theorem on the right triangle OPN. According to the Pythagoras theorem, PT is the abbreviation for Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is OP, so the square of the hypotenuse is OP squared, and it must be equal to the sum of the squares of the perpendiculars, that is to say it must be equal to NO squared plus PN squared. So in conclusion, we found out that according to equation number 1, OP squared equals to NO squared plus PN squared. OP is capital R minus 2, so OP squared is capital R minus 2 squared plus NO squared. NO is X, so NO squared is X squared plus NP squared. NP is 2, so NP squared is 2 squared, that is 4. So in conclusion, we found out that according to equation number 1, R minus 2 squared equals to X squared plus 4. Here we open the brackets on this side of equation number 1 and found out that R minus 2 squared equals to R squared plus 4 minus 4R, that is equals to X squared plus 4. We have 4 on both sides of the equation, so 4 will get cancelled. And we got that according to equation number 1, X squared equals to R squared minus 4R. This is according to equation number 1. And here we have an external notch between the circle and the quarter circle. And whenever you have an external notch between two circular shapes, then the straight line that joins their centers, in this case point M is the center of the semicircle, point P is the center of the circle. So the straight line that joins their centers together is MP, and according to the rule that I mentioned, this straight line must pass through the touching point of the two circular shapes. That is to say, it must pass from point L, that is the touching point or the point of tendency of the two circular shapes. That is to say, we can conclude from the rule that I mentioned that MLP is one straight line. So you can conclude from it that MLP is one straight line. MLP is one straight line. So what is the length of line segment MLP that is straight line? The length of line segment MLP that is a straight line is equal to ML plus LP. MLP equals to ML plus LP. ML, M is the center of the semicircle. L is the point of the semicircle itself. That is to say, ML is the radius of the semicircle that is equal to 2 units according to what is given as the question. Here, point P is the center of the circle. Point L is the point on the circle itself. So PL is the radius of the circle that is equal to 2 units according to what is given as the question. So in conclusion, we found out that ML equals to 2 units, LP also equals to 2 units. They are both the radii of the circle and the semicircle. So in conclusion, we found out that the length of the straight line MLP equals to 2 plus 2, that is 4. So MLP equals to 4, and because of the fact that MLP is equal to 4, we can relate to it as MP. So we know that MP equals to, for MP that is a straight line, it is equal to 4 units. MP equals to 4 units. Then I draw the right triangle MHP in this new page. But before that, we found out the length of MH. What is the length of MH? It's very easy to see that the length of line segment MH equals to ZO, that is the radius of the quarter circle, minus ZM minus edge O. I'll repeat again. MH, the length of line segment MH equals to ZO, that is the radius of the quarter circle, minus ZM minus edge O. So OZ is the radius of the quarter circle, ZM equals to 2, and edge O equals to 2. I repeat again, MH equals to OZ, that is capital R, MZ equals to 2 units, and edge O also equals to 2 units. So in conclusion, we found out that the length of line segment MH equals to capital R minus 2 is minus 4. So MH equals to capital R minus 4. So the length of this line segment MH equals to capital R minus 4. Then I copied the right triangle MHP in this page, and we implemented the Pythagoras theorem on the right triangle MHP. We just right now found out that MH equals to capital R minus 4. We know that HP equals to X. Here HP equals to X. And the hypotenuse MP equals to 2 plus 2, that is 4. The hypotenuse equals to 4 units. So we implemented, and the reason that this angle equals to 90 degrees is because according to our construction, from point B we drew perpendicular on MO. So according to our construction, this angle equals to 90 degrees and this angle also equals to 90 degrees. Therefore, this angle MHP equals to 90 degrees. This angle MHP equals to 90 degrees. Therefore, triangle MHP is a right triangle. So we can implement the Pythagoras theorem on the right triangle, triangle MHP. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, the hypotenuse is MP and the square of the hypotenuse is MP squared. That is equal to the sum of the squares of the perpendiculars. That is to say, it is equal to MH squared plus HP squared. MP equals to 4. Therefore, MP squared is 4 squared, that is 16. Edge M equals to capital R minus 4. Therefore, edge M squared or MH squared equals to capital R minus 4 squared. plus HP squared. HP equals to x, so HP squared is x squared. So in conclusion, we found out that according to equation number 2, 16 equals to capital R minus 4 squared plus x squared. We open the brackets on this side of the equation and found out that 16 equals to R minus 4 squared is R squared plus 4 squared, that is 16, minus 2 times R times 4 is minus 8R plus x squared. So according to equation number 2, we found out that 16 equals to R squared plus 16 minus 8R plus x squared. We have 16 on both sides of equation number 2, so 16 will get cancelled. And what is left from equation number 2 after we cancel 16? What is left is that in this side of the equation we have 0, that is equals to R squared minus 8R plus x squared. We added 8R to this equation, equation number 2, and we got that 0 plus 8R is 8R, that is equal to R squared plus x squared. Then we subtracted R squared from this equation, equation number 2, and we found out that 8R minus R squared equals to x squared. So according to equation number 2, x squared equals to 8R minus R squared, and we already found out that according to equation number 1, x squared equals to R squared minus 4R. Therefore, we created equation number 3. We have two expressions for x squared. For equation number 1 and equation number 2. Therefore, we created equation number 3 that states that x squared according to equation number 1 must be equal to x squared according to equation number 2. So x squared equals to x squared. So x squared according to equation number 1 is R squared minus 4R. Then it must be equal to x squared according to equation number 2, that is equal to 8R minus R squared. Okay? Here we added R squared to this equation, equation number 3. And we got that R squared plus R squared is 2R squared minus 4R equals to 8R. Here we added 4R to this equation, equation number 3, and we found out that 2R squared equals to 4R minus 4R is 0, and 8R plus 4R is 12R. So in conclusion, we found out that according to equation number 3, 2R squared equals to 12R. Here we divided this equation, equation number 3 by 2, and we found out that according to equation number 3, 2R squared over 2 is R squared, and 12R over 2 is 6R. So in conclusion, we found out that according to equation number 3, R squared equals to 6R. Here we subtracted 6R from this equation, equation number 3, and we found out that R squared minus 6R equals to 0. So here we took a common factor of R from this equation, equation number 3, and we found out here what is left from R squared after we took from it R as a common factor. What is left is actually R. And what is left from minus 6R after we took from it R as a common factor, what is left is actually minus 6. So in conclusion, we found out that according to equation number 3, R times R minus 6 equals to 0. So here we have two solutions that are possible for capital R. Either capital R will be equal to 0 or R minus 6 will be equal to 0. But capital R can never be equal to 0 because capital R is the radius of this quarter circle that it must be a positive number. So we cancel this solution and we left only with the other solution that capital R minus 6 equals to 0. We added 6 to this equation and found out that capital R equals to 6 units. That is to say, the radius of this quarter circle equals to 6 units. And what is the area of this shaded shape? The area of the shaded shape or the shaded area will be equal to the area of the quarter circle minus the area of the circle minus the area of the semicircle. I repeat again, the shaded area, the value of the shaded area equals to the area of the quarter circle minus the area of the circle minus the area of the semicircle. The area of the quarter circle equals to pi r squared over 4, that is to say it is the area of any quarter circle. It is the area of the circle that is pi r squared over 4. While the area of the circle equals to pi r squared, but r equals to 2, so pi r squared is pi times 2 squared, and the area of the semicircle equals to pi r squared over 2, and r is 2, so it is pi 2 squared over 2. So R, the area of the capital R, the area of the quarter circle equal to 6. So R squared is 6 squared, that is 36. So in total this expression equals to 36 pi over 4, that is the area of the quarter circle, minus the area of the circle, that is pi 2 squared. 2 squared is 4, so in total this expression equals to 4r, so it is minus 4r, that is the area of the circle, minus the area of the semicircle. The area of the semicircle equals to pi 2 squared over 2. 2 squared is 4, so in the numerator we have 4 pi over 2. 4 pi over 2 is 2 pi. So in conclusion, the area of the semicircle equals to 2 pi, so we had to subtract from the total area, the area of the quarter circle, the area of the semicircle, of course. So in conclusion, the area of the shaded area, the value of the shaded area equals to 36 pi over 4. 36 over 4 is 9, so in total this expression equals to 9 pi minus 4 pi minus 2 pi. 9 pi minus 4 pi is 5 pi, and 5 pi minus 2i is 3 pi. 5 pi minus 2 pi is 3 pi. So in conclusion, we found out that the shaded area here equals to either 3 pi square units, or in terms of numbers, it is equal to 9.42 square units. Okay? Thank you very much.